This is the lecture on physical development. We're going to focus in on brain maturation. So we'll start by understanding the principles of physical development and then look at how the brain develops, specifically how neurons communicate with one another and what that means for learning. We'll start first with the 6 overall principles of physical development, and then we'll get more into those, the communication inside the brain and what that means for learning. Okay, so 6 principles of physical development. These do come from your book and are outlined in your lecture notes and your active reading questions. So the first principle, different parts of the body mature at different rates. Okay, this isn't really all that surprising when you think about something as obvious as puberty, right? That doesn't happen until adolescence. So different parts of our body are going to mature at different rates. And there are particular growth patterns or curves that exist for all of the different areas. Okay. The next 2 principles I have together because I find that sometimes we confuse them. And what's more important here, I would say, is understanding that this happens within not only brain development but also physical development. And it's the normal developmental trend that we see when we look at physical growth. Okay? So the first one is differentiation. The second one is integration. And this should ring some bells from your quiz, right? Yeah. Functioning becomes increasingly differentiated. What that means is we go from general to specific. So if we want to think about it in terms of brain development, we're going from a lot of areas of the brain that are not quite 100% specific yet in their roles to more specific in the role and what they can and what they actually do. Okay? And then that is also true for physical development. So you can think of it in terms of reaching and fine motor skills. When infants are first learning how to reach, they're kind of like this, right? And then pretty soon they can get more specific and they can be able to move and they can soon grasp with just their finger. So instead of a very sloppy this, I can go in and get my Cheerio and eat it from my high chair. Okay. So general to specific, and you can see how this ties in with coordination now, with integration. So it's not only that it's moving from general to specific, but that everything is working together. It's coordinated. Okay. So the different areas of the brain are communicating to one another more quickly, more readily, and in our physical development, we have more control. Sound good? All right. Let's see. The third, no, we're on the 4th principle. Every child follows a different growth curve. So that's really important. Walking, the first steps. When children walk, there's a lot of individual variation that exists in that between individuals. So this should remind you of one of our key issues in the whole field of child development, right? Where we talk about things that make us the same and things that make us different. Physical growth is a big one that has a lot of individual differences. Okay? So if you are talking to a parent, let's say about a child's coordination, or if you're in an early childhood education classroom and it is walking, you can reassure them that every child kind of does this on their own and that it's okay if some of the peers are walking yet and that this child isn't. Yeah, it's fine.
I have a quick question on that because my parents actually put me through, they had me done some psychological tests because I never crawled as a child.
Oh yeah, some kids
I just went straight up to walking, and they said that my brain actually will learn differently. I learn backwards.
Really?
Because what they said is they say that I have a learning disability because I learn backwards. Right?
Some kids totally skip crawling.
And then go to the beginning as opposed to a linear path.
I would stick more with just that it's a physical development issue and your body just, this is the way that it, is easy for you. Some kids scoot, the one leg up and then they kind of like move their butt along the floor. Some kids crawl backwards and not forwards and then stand and walk, and so everybody's a little bit different in this. Culture also affects walking and first steps, which is really interesting. There are tribes in Africa, and I don't know the name of the tribes, I'd have to look them up, very indigenous people who dig holes in the ground and put their babies into the holes and then cover it with dirt. So they're like half in the ground and half not. But the sand is kind of like mushy and soft, and so they develop leg muscles earlier than children do in the US, and they'll take their first steps 3 to 4 months earlier. Yeah, isn't that neat? I don't really suggest that in our society. You might get arrested. Yeah, okay. Number 5, physical development is characterized by both qualitative and quantitative changes. Here's another one of those key issues, right, from the first chapter, our first lecture. So what is the difference between a qualitative and a quantitative change? What are those?
One's gradual and one is major changes.
Yep.
That you see right up front and others that you see.
Yeah, so small little growth or big changes, right? Small growth you'll see in weight, when children are gaining weight, when they're growing larger, inches, small, okay? You don't see that every single day, it just happens over time. But then if you have gone to see a family member that you haven't seen in maybe 4 or 5 months, it looks huge. You're like, what happened to you? Okay, I had to hug my little cousin up at Christmas. I was like this, and I was like, when did this happen? And I swear it was in like 6 months. Okay, so it seemed bigger to me, but that would be a smaller growth. Okay? And then there are changes that are much bigger. Puberty is an example. So a woman's first menstruation, that's a big change. Okay. All right, the last one here is that children's bodies are dynamic systems. And this is really the most important one. I would highlight it, I would star it. What this means is that everything is working together. Okay, and it's complex and complicated. It's a dynamic system. We are a huge being of interconnected parts that communicate to one another. If one thing is off, it'll mess up something else. Okay, everything is working in conjunction, and it's a big dynamic system. So we think about that from education or from parenting perspective. And you should know that if one thing is kind of going wrong, that there's probably going to be some other issues that come from that.
Always the ripple effect.
Yes, a ripple effect, sure. Absolutely. So we're going to keep these principles in mind as we look at brain maturation, and then also as you revisit physical growth in your texts. Okay? So on your handout here, you have the cover page there that came from Ray on the glial cells, so that's a really good, helpful reminder for you, a good handout. What I want you to do is flip to the next page, and we have the structure of a neuron, and right now it's blank, okay? So I want you to use this to help you learn and retain this information. So I know that we're in college and I'm giving you a handout, like a ditto, if anybody remembers I'm being called up, right?
Still called.
Yeah. Yeah. To be explicit, what I'm doing here is I'm trying to give you a framework to organize your knowledge. So this is an organizational tool. And if you are teaching, you could also use similar graphic organizers, or they don't even have to be pictures, they can be words, outlines, anything that can help your students to kind of organize and give a framework for what you're about to go over. Okay, so that's what this is. You can leave it blank, you can label it now, you can use it to quiz yourself later. Okay? So let's take a look at the brain and its development, and we're going to focus in on the tiniest little portion here. So we're going to look really small at neurons and how neurons communicate and what that means for learning. All right, so I'm going to talk about neurons and neurotransmission of information using analogies, okay, and I invite you to also join me in that. So first we have the actual structure, it's the neuron. Okay, so I have a picture here of 3 individual neurons. Okay. These are brain cells, they transmit information to other cells. They are the super duper most important cells that we have in our brain. responsible for complex thought, breathing, everything that we do. Okay, so you think of the neuron as the major cell. So in our analogy, each of us are going to be neurons. Okay, so I want you to think about it in that way. I am a neuron. Chance is a neuron. Bryce is a neuron. Thank you. I'm getting there. Everybody is a neuron. Okay? The next piece that we want to understand is the axon. That's the arm-like part of the neuron. And this is what sends information to and from other neurons. So here we have a neuron. The axon is going to be this long piece that runs off the neuron. So you can see there are lots of axons shooting off of each one. So if I am a neuron, my arms are the axons. They're the arm-like parts. Okay, so everyone has a cell body, a neuron, and we've got axons. With me so far? All right. The next piece that you want to know is the dendrite, and these definitions should be online. Okay. The dendrite is going to be what actually transmits the message between the two. So it receives and it sends, and you can think of the dendrite as your fingers, or my fingers. These are dendrites. So I am an axon, I'm sorry, a neuron. My arms are the axons, and here are my fingers, and they're the dendrites. Okay, and you could also do the same thing with feet, legs, and toes, if you want. All right, the synapse is the junction between the two neurons. So it's the area that exists between myself and Stephanie, or myself and Shayna.
You did it.
All right, so I'm a little bit closer here to Stephanie than I am Shayna, or I am to Chance. So the closer you are, that there's an actual probability that I might send a message to her. So you have to be close to one another. Is that clear? So I'm not going to be sending any messages to Kenny back there. I'd have to go through all of you to get there. Okay? Now it looks like in this picture that these actually touch, but they don't. The synapse is actually a space in between. So if I've got two sets of dendrites coming in, there's a little space in the middle. That's going to be the synapse. And that space is important, so they're not touching. Okay? We've already talked about the glial cells. They're the support cells. So if I am a neuron and I've got an axon, what do you think the glial cells would be on me? In our analogy.
If you were what?
I'm a neuron, I have an axon, dendrites. What are the glial cells on me? My clothes. Yeah, thank you. It's my clothes. Okay? So these are the glial cells. Okay? This makes up what we call the myelin sheath. And we know how important the glial cells are from our YouTube video. This keeps me safe, keeps me insulated, warm, speeds me up. This is the support. Okay? Because I would be a lot more vulnerable if I was naked. Let's just be honest. Right? It would be a lot worse. All right, so on our diagram here, you can see all this surrounding, almost like fatty tissue, is the myelin sheath, and that's made up by those glial cells.
So the glial cells make the myelin sheath.
They do, yep, absolutely. So we have the structure of the neuron down. What we want to do is now talk about how the neurons communicate with one another. Okay? So what actually is happening when our neurons are communicating? It all starts with ions. We have ions in our system, positive or negative, okay? And they flow in and out of our cells, and that changes electrical messages, or starts electrical messages. So the movement of those ions, either positive or negative, will send a charge. And all neural communication is are little electric charges. little messages. You can think of them for simplicity's sake as a little electric kind of shock that goes through the system. It lights up. Okay. So it all starts with the ions. When you are a neuron and you're just hanging out, you are in your resting potential. So you can think of it as simply that I'm resting, I'm chilling, everything's cool. Not doing anything, just hanging around. I'm in a resting potential. So if it's me and I'm the neuron, right? Just like, what's up? Just here. Things are good. Just hanging out. I'm more negative than I am positive. And that would make sense, right? Because I'm just like hanging out. Tired. Just here. A little bit down. So I am a neuron and I'm in my resting potential. A little bit more negative than positive.
Bless you.
So does anyone want to hypothesize what happens to me, the neuron, from resting potential? So I'm hanging out here. What happens?
Well, the next neuron will either send a message through the synaptic gap to your dendrite, and it'll hit, and then it'll have that deciding of firing or not, and go into action potential, and
Yeah.
fire through axon.
Sure. So something's going to excite me, right? Something's going to make me excited. We call that the action potential. So I'm just hanging out. Something's got to excite me. Now, it either can be another neuron's message, or it can be a shift in the ions. Okay? So it can be one of the two. Now, a lot of times, another neuron's message is going to create a shift in the ion as well. Okay? So my ions are going to go from negative to positive. So here we have the action potential. We actually call it depolarization. It's when the neuron shifts from negative to positive. Okay, depolarization. This takes us out of our resting potential and creates what we call the action potential. Action is the movement, okay, the signal. Go, go, go. Action. So I'll demonstrate it up here, and then also with myself as a neuron. So we start off, there's the cell body, we call that the neuron, and it's actually sodium ions that run in and out of the system. So sodium being Na, salt. Okay. So what might happen, well, let me ask you that question in a minute. Okay, but remember that it's actually salt, it's sodium. So I start off, I'm more negative than I am positive, I'm resting, and all of those sodium ions flow in to the body. So we have the action potential. Okay? It gets excited, and it sends a message down the axon. Okay, so let's look at it again. We have the cell body, resting potential. It's more negative here than it is positive. There's sodium ions that flow in. It excites the cell. And that's the depolarization, which creates the action potential. So if it's me, I'm hanging out, everything's cool. All of a sudden, some sodium rushes in. I get excited, and I send a message. Okay?
We see that again?
Sure. So I'm chilling. Some sodium rushes in. I get excited, and I send a message. Good? All right. So back to that question I had here. Sodium is actually salt. So what happens when you're dehydrated? You do have lethargy. Yep, definitely. Yeah, so you get a little bit more tired, you get a little bit more confused, and when you get into real dehydration, you can have some dementia. Right? Sodium is a big part of that system. when we sweat, it's salty. We're losing a lot of these ions that are going to be important. It's more complicated than that, of course. Much, much more complicated than that. And that's part of this whole thing being a dynamic system. Okay. All right. So how do we feel here about the action potential? The message goes, and then what happens? Well, we need to talk about what goes on at the synapse. Okay, so remember the space between my fingers or the space between dendrites. So up top here you have the sending neuron, the action potential, and then it's showing one little spot, one little dendrite that's close to another cell body. Okay, and it's going to zoom in on that right here. So this would be a finger, and this is another body, another cell. Okay. What happens is it actually sprays out tiny little chemicals called neurotransmitters. Okay, so when I go like this, it's because I'm actually spraying you. Okay? I'm actually giving you something. Magic. I'm a sorcerer. Okay. So, but this is what our brain is doing. So it's sending out neurotransmitters. Now, those cells that I'm close to are going to get some of those neurotransmitters and absorb them. And that's going to change their behavior, their mood, emotions, and it's going to excite that person's, then they send out another message. Okay. Neurotransmitters actually have their effect on brain functioning and behavior when they're in the middle here, when they're in that synaptic gap, because they're getting absorbed by the system. Now the message keeps going. If I excite Chance here, he might get Shayna, who's going to hit Stephanie, and it's going to keep going, right? But while some of that is floating in the air, it's going to change our behavior and our emotions and really have an effect on us psychologically. Okay? So neurotransmitters, yeah.
How exactly do we know that all of this, like how?
They have very fancy microscopes. Just brain research. Yeah.
Can we like actually see that happening though?
Yes, they
Like you can watch the activity in someone's brain and observe what's happening.
That's why we'll find things like the bipolar and the ADD and the ADHD, because if the neurotransmitters do not fire correctly,
Exactly.
then the information gets skewed, and then those emotions and those functions don't.
Yep.
Really
So
correct.
there are lots of different types of neurotransmitters that are responsible for a lot of different things. The example that I like to talk about is the one that we know the most about, and I think we can all kind of connect to, which is depression. Okay? So I'm not saying we're all depressed. What I'm saying is there's a lot of advertisement for drugs for depression, and a lot of people who do suffer from depression. So let's talk about what depression looks like on this neurotransmitter level. Okay? There are the most common drugs to treat depression are called SSRIs. Have we heard of these? Prozac is an SSRI. Is a good example.
Should we write this down? The SRI?
Only if you are just really excited about learning SSRIs. Then you should. Okay, so SSRI, selective serotonin reuptake inhibitor. Okay. So selective serotonin, we know it's going to work on the serotonin, the neurotransmitter that makes us feel good. Reuptake inhibitor. So I shoot off a bunch of serotonin, okay? And while it's out there in the system, that's when it makes people feel good. The more serotonin in the system, the better you feel. Now there's a natural process where once I'm done shooting it off, I pull away. So I close the doors. Okay. But while it's going, I stand here for a minute, I can take some of it back. Reuptake. And then I close the doors. And then you're going to absorb some of it. Okay? Good so far? All right, so what do you think this does? Reuptake inhibitor.
It blocks the door so that serotonin can't be basically reabsorbed back into the...
Right, it closes the door. says, no, we're not going to pull any more in. So now there's more serotonin in the system. So we feel happier. So a little drug comes floating in, and it makes this close, blocks it. Now there's more serotonin, people feel happier.
Can you build a tolerance to antidepressants?
Yes, you can build tolerance, yeah. And there are other antidepressants that work on different neurotransmitters like dopamine and some other things. This is just one.
But you can build like a tolerance to all?
Well, so that's why doctors oftentimes will switch medications. So that, you know, if you have built a tolerance, you can switch, deregulate the system. Yeah, Kenny.
So how do they test people for that? How's that work? Like when
Do they?
like I don't know.
No, they don't.
You just tolerate
So, I mean, they can, but they don't.
Yeah, I got you.
So people can get antidepressants really quite easily, and doctors prescribe antidepressants quite easily. Now this is changing a little bit more recently than it has in the past.
My daughters all have issues, and her psychiatrist is now doing genetic testing.
Fantastic.
So that they can pinpoint exactly which ones are not connecting and exactly what things they need to prescribe for, so they're not misprescribing.
Good. And this is new though.
Right.
So this hasn't been common practice.
No, it hasn't. If I could add,
Yeah.
I'm going to share something. I was depressed, and
It's okay, Ray.
I went through. My doctor, we went through 7 different kinds of antidepressants before we found one that actually worked for me, and it was a really difficult process because you can't just stop an antidepressant. You have to wean yourself off and then build yourself up on another one.
There's anxiety around some of that
Yeah,
too.
it's really horrible, but yeah, it's I'm glad it's changing.
Why hasn't it been that way before? Like, why is that like a new thing that's changing? It seems like we would have done that first. before.
Yeah, I think the expense of the tests, the science is better now.
Well, a doctor that my mom works for deals with teens with depression. They haven't done the testing because it takes too long, and if the teen really is depressed, they want to get them started right away because it takes a lot for a teen to come out and well, I'm depressed, so I need help.
To even know that.
Yeah, so usually it's as soon as it happens, they want to get you started on something.
Yeah.
That way you're starting in the system and getting it going, and the testing takes
Sure.
a little
Yeah.
while.
Yeah. So, because I used to be an intern for a couple of hospitals and things like that, and actually, I have a friend who works in the psych ward for Swedish, and a lot of the times what they'll do is
You have
especially
to
for
treat.
teenagers, you need to treat it. And that's
Sure.
their main purpose is
Totally.
to treat, and also the fear of when someone comes in and says they're depressed, the next step that a lot of people that are depressed go into is suicidal attempts. And so they want to prevent that. So they kind of put you on a cocktail of drugs and
Yeah,
they're here,
and then try
cocktail,
to figure out what
try to
works.
figure out something.
Yeah, totally. Yeah. But just the availability and ease of getting a prescription has been a problem, not only for depression drugs, but also things that treat ADHD, so on and so forth. Okay. All right, so that's the SSRI. Just a real quick side note, if we flip this over, what is it when you have too much serotonin in your system? It's manic, yep. So you're very excited. It's the other side of bipolar. But there's drugs that you can take that will do this on the street called uppers, ecstasy. Yeah, so that's what E does. So E says, I'm going to give you so much serotonin. But what E does is it releases your natural serotonin. And so the next day, people are very depressed because they've got no serotonin in their system. People who are continually using drugs like ecstasy will deplete their body's natural resources of serotonin.
So at this point, we did a class activity where we demonstrated neural communication, and then also where we labeled brain structures and what they're responsible for, the hindbrain, midbrain, and forebrain. So you want to take a look at that in your text and in your lecture materials.
5 minutes left here. I want to take a look at a few of these developmental changes that exist in the brain, just to highlight the ones that are important that you want to keep in mind. Okay, and we'll come back to the application piece thereafter. So, in the 4th edition, this is page 156, in the 3rd edition, 109, but we couldn't find it in the new edition. But these are, it's a chart of developmental changes in the brain. These are on the lecture notes, right? I was just looking. They're on the lecture notes, so you have this available to you. Okay? So what this is how the brain changes as we age, and some things that are important to keep in mind from an education perspective. So prenatal development, structures are forming, neurons are forming, the cortex is maturing. Infancy, we're starting to get connections, okay, between our neurons. What we just did here, we're starting to connect. Synapses grow in density, so the amount of synapses. And then the brain becomes differentiated. We already talked about that. Okay. Can someone remind me of what differentiated means? Heather.
You kind of specialize instead of thinking about everything. You just think
Yep. So the different areas are going to become more specialized. And then myelinization begins. What is myelinization? Yep, you're putting clothes on. Okay, speeding up. Here we have some slides of neurons from different age periods, as well as just the brain development in a cartoon drawing. But if we look at this one, A, this is where we have the newborn. Okay, so, and then we can go all the way up through 24 months. So you're seeing how those neurons are becoming, there's more of them, more density, more connections. In childhood, we have synaptic pruning. Yeah.
Is the brain active while it's like developing in the womb, or is it just like developing?
It depends on the stage. So early on, just developing, but in your 3rd trimester, there's definitely activity.
Really, that's crazy.
Totally.
That's pretty crazy. So your baby is like actually thinking.
Yes.
Essentially,
Neurons
probably
are
like
fire.
processing information.
Yep,
That's
totally.
crazy. So they start learning.
Yeah, and there's some
now.
really interesting research on memory from in the womb.
Oh, is that
It's really just
possible?
recognition of voice,
Music.
music, tone, things like that.
That's crazy.
Yeah. Okay, synaptic pruning. Ray mentioned this very quickly during the YouTube clip. So synaptic pruning is where we get rid of things that we aren't using. So connections that have been made or ones that haven't formed connections, they go away. Get rid of them. So an important point for education. A lot of the content that you learn, the rows of neurons, they go away. Are You Smarter Than a 5th Grader demonstrates this every night on TV. Right? We do not remember the content. It's gone. We had it at one point, but it's gone. Okay, so what is more important, content or how to learn?
How to learn.
How to learn. I mean, I'm giving you the answer here, but yes, how to learn. Processes of thinking are more important than content because the content's going to get pruned away at a neurological level. Okay? Myelinization continues, new synapses to reflect new learning. In adolescence, we still have synaptic pruning happening. This is the one I want you to think of. The cortex matures. Their brain is not mature in adolescence. It's finally kind of coming into its own and finishing off this process. Okay? So this is especially true in the prefrontal cortex where we make decisions. So adolescents make bad decisions in part because their brain is not mature yet.
I read somewhere that adolescents will make decisions based on emotion, not based on logic.
Yeah, it's reasoning. It's all happening in the prefrontal cortex, and it's just not there yet. So do not hold adolescents to the same standards as you would an adult. Their brain is not there yet. Just like you wouldn't hold a child to the same reasoning skills or decision making. Okay? It's not there yet. On a neurological level. Okay? All right, so our applications, we've already covered these. So it's not anything new, right? Learning is happening all the time. It's not planned. They're soaking things up. They're making connections all the time. I say maintain optimism. All people learn. We can get really frustrated with our students, but we know what learning is. It's just connecting neurons. You can individualize instruction for children with various neurological exceptionalities. This is also true for those who might have been exposed to any teratogens while in the womb, so drugs or alcohol. Their brain chemistry is going to be different. Teaching about responsibility, consequences of behavior, how to learn instead of just content. That's a big one. Being patient, having faith in children's resilience. This is especially true after abuse. This just connects in with all children learn. And the last one is to shield adolescents from risk, okay? Because they will make poor decisions. Biologically, they will do this. Yeah, I don't know how, I'm just telling you to do it. Okay? So what we did, what we didn't do, if you guys have any questions, please don't hesitate to ask.
Here's your summary slide, what we covered, what we didn't cover. Make sure that you're still paying attention to these objectives here that we don't get a chance to cover in these mini lectures. You're all still responsible for that material.